about KISS, a fast KNN-based importance score for subspaces, a short paper at EDBT 2021. Our problem is the curse of dimensionality. You may say that's quite an old problem. There are already subspace clustering algorithms out there and subspace search algorithms, but none of them fulfill the properties we desired. One of the main problems is that you can't use distance measures in high dimensionalities. Also, there are lots of irrelevant attributes, and often the runtime grows exponentially with the number of dimensions, as the number of subspaces grows exponentially with the number of dimensions. As always, we know that expert knowledge is quite expensive, so we shouldn't use too many parameters, and we want reproducible results. Additionally, there is no one-fits-all solution, as we nowadays have heterogeneous data and also redundant dimensions. So none of the algorithms out there worked for us. That's why we created KISS. For that, we don't use any distance measures in high dimensionalities. We only use the k-nearest neighbors in one-dimensional projections of the data. We create a score instead of a binary decision between relevant and irrelevant, and our runtime is fast. We're only linear in the number of dimensions and n log n in the number of points. We're fully automatic, so we don't require any user input, and the algorithm is deterministic. The main new thing about KISS is that we create individual scores, so every point can have a different distribution of important dimensions. But what is an important dimension? If you take a look at a cluster, well, you see here the cluster in the 3D space is also detectable in the 2D space. And also in the one-dimensional projections here, you can already see the cluster structure. But if you have a subspace cluster, which is not in the full dimensional space, but only in the XY axis or subspace, you can still detect the cluster in the X and Y axis, but the Z axis is not important. The points here are uniformly distributed and don't give us any input. So we say that though this dimension is not important, so an important dimension is a dimension where a point probably lies inside a subspace cluster. For that, we regard the KNN in every dimension separately. That works. We have the mathematical idea also in the paper. Of course, it's not perfect, but that comes in the discussion. So how does it work? We start with an empty matrix with dimensionality n times d. So for every point and every dimension, we will have a KISS score at the end. So we loop over those. And then we look for every point. We look at the KNN of it in this one dimension D. And those points Q, all of them get a point score. And that point score depends on how often they occur in the one-dimensional KNN of other dimensions regarding this point. We simply sum that up, weight it by its distance, and do some normalizing stuff around that. Or simpler said, if we regard a point P and we want to know how important the dimension D is for P, we look at the points in its one-dimensional k-nearest neighbors set in this dimension. And yeah, if you already know those points from other one-dimensional k-nearest neighbors sets for this point, then maybe this dimension is important, as it is in a subspace cluster in those dimensions with those points which occur often in the KNN. How does it look like? We have many experiments based on a base case experiment, which consists of 3 clusters and some noise. The clusters are, of course, all only in subspaces. In detail, in the first few dimensions. The second cluster is in the last few dimensions. The third cluster is in some dimensions here, and the noise is, well, is noise in every dimension. What we see here is on the y-axis, the sum of KISS scores for the points regarded, while we regard only the points of one cluster, respectively only points which are noise, in each of the diagrams. And you can see that the KISS score quite good correlates with the with the dimensions the cluster was created in. If you look at a point separately, the typical distribution of KISS scores ordered by their size looks like this. So we have only a few dimensions which are very important, in which the point lies in a cluster, and many dimensions where, well, those are not important for the point, and the points in those dimensions were created uniformly. To be able to compare ourselves, nevertheless, we need a binarization, but it is intended that you can use those scoring we get here. For the binarization, we made two possibilities. We can simply binarize it with a threshold. So the higher the point is, the score is, the more probably the dimension gets detected as important. And we also have a more complex binarization method, which works with 3 thresholds, which are nevertheless set to the same values for the experiments. We then compared our results with clique and surfing and were quite content. So we have a high precision for KISS, where the 3 columns imply different binarization methods, and not so high recall, which is clear because KISS and surfing, which are here the 3 columns for different parameter settings, they detect much more dimensions as important than we do. So it's a trade-off. Of course, we also get a quite high precision or a high recall depending on the threshold, but we decided for a threshold of 0.2, which worked quite good, and we thought the precision is quite more important than the recall. One problem of KISS is that, if you have a data set like that and a point which lies in every one-dimensional projection inside a cluster, it's difficult to say which dimensions are important. But as the dimensionality increases, well, that only happens very rarely, that a point really lies in every projection inside a cluster. So what are the applications for KISS? Of course, clustering. The idea is based on clustering, and we already tried it out, and maybe there's a follow-up paper someday. You can just weigh the distance matrix of points with respect to KISS. So just multiply it and you get this. You have here a Euclidean distance, and if you multiply it with multiply every dimension, the distance in every dimension, with the KISS score in this dimension, you get a matrix where you can much better detect the clusters, which are those blocks on the diagonal here. And it already delivered some good results if we combined it with distance-based clustering algorithms like hierarchical or spectral clustering. So here we are the last column, and I'd say that's quite promising. You can also use KISS for outlier and noise detection, as there the KISS is quite low for every dimension. You can use it for analysis of all kind if you have high dimensional data. You could also save space by deleting not important dimensions. So be creative and use KISS, a fast KNN-based importance score for subspaces.